Okay, I think we are live. All right, so hello everyone and welcome to another session of the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I'll be your host this day. This is webinar number 113, and we're having Martin Jung as a speaker. Let me tell you some things about him. He did his PhD at Siegen University in Germany. And this was followed by postdocs at Valencia, Dortmund, and Munich. He is currently at Torino, where he has a position of assistant professor, and he's living his dream of being surrounded by Italian food all the time. So today, Martin will tell us about important facts about the processes involved in the B meson anomalies. So we are thrilled of having him as a speaker. So before we begin, as usual, let me remind the viewers that you can ask questions and make comments using the YouTube live chat system. And we will pass these questions to Martin at the end of the talk. So we're all yours, Martin.
Yeah, thank you very much for the kind words and the invitation, and especially also the artwork for the seminar. I find this very impressive. Yeah, so I'm going to talk about precision analysis of B to C transitions. So, so we're talking about quark flavor violation, essentially. And in the standard model, quark flavor violation and CP violation are both parametrized by the CKM matrix. And this is an extremely constraining framework. And you have just one phase responsible for CP violation. And the confirmation of this picture to give an uncertainty of something like 5 to 10% was basically the picture you see here, where all these different constraints overlap in this area here. And especially the band from kaon physics, which is this mint green one, agrees with all the information from B physics, which is all the others here. And this led to a Nobel Prize to Kobayashi and Maskawa a couple of years ago. And so far, we have seen impressive confirmation basically everywhere. There are a couple of tensions or anomalies, and about some of them I will talk a bit. But overall, all of this works perfectly well. But in fact, it works a bit too well in the sense that we know there must be more, right? So we have indirect observations in astrophysics, especially where we know that the particles that are investigated here, or the class of particles, makes up only this small slice here of the overall matter and energy content of the universe. And there's also something called the baryon asymmetry of the universe, which is related to CP violation that we cannot accommodate in the standard model. And so the question is, where is this new physics, right? And three of the main strategies to search for it are shown here. The first is to use direct searches, like at the Tevatron or the LHC, where the idea is basically to collide particles at higher and higher energies and try to produce the new particles directly in the laboratory and to analyze their decay products. And the problem here, to some extent, is that the maximal energy is fixed. So you can only go to a certain energy that your machine is capable of. On the other hand, it has the advantage that when you see something, you know immediately where your new physics is. So you see a resonance, for instance, with a certain invariant mass, and you can get a lot of information from analyzing this. What I will talk about are indirect searches, and more specifically flavor violating indirect searches. And here the idea is to analyze processes to very high precision and to look for effects that appear in loops, basically. So you do not try to produce new particles that are very heavy, potentially directly in the laboratory, but you're looking for indirect effects that these have on interactions between known standard model particles. And the sort of disadvantage is that you don't have a clear-cut interpretation necessarily when you see a deviation, but you have a lot of options how to interpret this. On the other hand, your maximal reach is really flexible, and it depends only on the precision you can reach experimentally and theoretically. And you have another class of indirect searches where you analyze flavor diagonal processes. And here you have, for example, EDMs, so electric dipole moments, or this by now famous G-2 anomaly, and so on. And the recent developments in experimental techniques, and especially the advent of the LHC, really made for a new era in particle physics. So the things we're discussing nowadays are qualitatively different from what we did, let's say, 10, 15 years ago. Regarding the B2C transitions that are the focus of this talk, they are flavor violating transitions, right? So a beauty quark goes into a charm quark. And so in the standard model, they proceed via the weak interaction. And they have a coupling constant associated with them, which we call VCB. And this is a fundamental standard model parameter that can only be found or determined from such transitions. So this is already one major motivation to look into these transitions. They dominate actually the lifetimes of the singly heavy ground state B hadrons, so the B meson or the lambda B, for example. The lifetimes are completely dominated by this transition. And as in all physics processes, we are interested in hierarchies, but in this case, maybe even more than in others, because here we have essentially 4 or maybe even 5 relevant scales that enter the problem. The highest scale shown here is where we suppose new physics to be. This is potentially at a level of a few TeV or even higher. And then we can use the hierarchy between this scale and the electroweak scale, so the scale where the Higgs lives, the top, and the W and Z bosons, to formulate effective theories that model independently describe new physics. At the weak scale, we have, as I said, especially the W boson that transmits the weak interaction. And we can use the fact that this is still much heavier than all the quarks and leptons involved in the process that we are discussing to formulate an effective theory where we do not consider the W as a dynamic degree of freedom anymore, but we consider local fermion operators that then transmit the processes we're interested in. And we have 2 classes here, the semileptonic and the non-leptonic ones. And about the non-leptonic ones, I will only talk about at the very end of the talk. And finally, we can also use the fact that the B quark, and to some extent also the charm quark, is much heavier than the typical scale of QCD processes to use a so-called heavy quark expansion. And we can use this to determine the matrix elements necessary for these transitions. And I mentioned already that we have some tensions here, and they are in B2C tau nu, but also in B2C L nu, where L is a light lepton, and also in this non-leptonic process that I will talk about at the end. So leptonic and semileptonic hadron decays are of special importance in the determination of these coupling constants that enter that constitute the CKM matrix. And that is because the transition or the amplitude for such a process is just this coupling. Then you have a factor of G Fermi, which is essentially 1 over the W mass squared that stems from this propagator here. And then you have a hadronic object. But compared to non-leptonic objects, this hadronic object is much easier. So you have either a form factor that I will talk a lot about or a decay constant. And this allows you to determine basically 6 out of 9 or even 7 out of 9 of these moduli of the CKM matrix elements. And in the standard model, an important property of the W couplings is that they are lepton flavor universals. So they don't differentiate between electrons, muons, and taus. Beyond the standard model, we can use these modes in the case of leptonic decays, especially because here the standard model contribution is additionally suppressed by the lepton mass squared. And then you can have a relatively large new physics influence. But in the semileptonic decays that I will talk mostly about, you expect small or at most moderate effects from new physics. So here you really need to understand the standard model very precisely to differentiate new physics effects from standard model contributions. And the key advantages of these modes are that you have large rates. So for example, inclusive mode B to anything with a charm decay and an electron and a neutrino is like 10% of the total rate of a B meson. You have minimal hadronic input, so you have these form factors and decay constants, but these are determined or can be determined systematically, and especially this can be improved in the future systematically by lattice calculations especially. And they are already sufficiently complicated that you have things like differential distributions. So you have already a significant set of observables and can analyze different features of these modes and thereby differentiate between different new physics contributions. In semileptonic B2C transitions, we have the so-called VCB puzzle, and we have had this for over 20 years already. And this is a difference between the extraction of this parameter VCB from inclusive decays, where you do not analyze the specific hadronic state in the final state, but only consider everything with a charm quark and look for an explicit lepton and neutrino. And there you get this value here for VCB. While from the exclusive mode, so B to D LNU and B to D star LNU, you get this green and pink band basically, or you did get this in the past. And you see that the best fit to these exclusive modes lies here and is very far from the inclusive ones. On the y-axis, we have VUB that I will not talk about in this talk, but I will update basically the x-axis later in this talk. One reason why there is a lot of interest in these transitions is the anomaly we see in B2C tau nu transitions. This is a anomaly in R and or RD and RD star, basically, where these R ratios are ratios between B decay mode into something with a tau lepton and the B mode into the same hadronic system with a light lepton. And I show here the one for B to D tau nu and B to D star tau nu. And you see there have been measurements by Barbar, by Bell, and by LHCb. And the global average looks something like this. So this is this red ellipse, while the standard model predictions are also very precise because we have this ratio here where a large part of the uncertainties cancel, and you see it's quite far away from this red ellipse. So this is something like 3 to 4 sigma. There are a lot of other observables that I will not go into detail here. But one thing I want you to note is that there is only one result so far that is more than 3 sigma from the standard model, and this is this Barbar measurement, while the others are closer to the standard model. But nevertheless, this lighter blue ellipse and the orange band are both averages of several measurements, and all of them disagree with the standard model prediction by something like 2 sigma or so. And I will not go into detail for this anomaly, but I just want to make some general comments. The first comment is that this is a huge effect. This is much larger than anyone would have expected in a semileptonic decay. And so this is something like 15% of a tree decay on the branching ratio level. So at amplitude level, you need something like 5 to 10% if you have interference with a standard model, or something like 40% if you do not have interference with a standard model. And the only reason this is not yet completely excluded is because we have taus in the final state that are notoriously difficult to measure. So what can we do about this? The first thing, if we see a deviation with a standard model, is always we check the standard model prediction. And I will talk quite extensively about this. And the upshot of this is that the uncertainty is nowadays a bit larger than what was assumed when the first Barbar result appeared, but not so much larger that the anomaly would go away. So the value here is already an updated one, and this is, to the best of our knowledge, the uncertainty of the standard model prediction nowadays. Then you can do a combined analysis of all these observables that you have here, and there are 100+ papers that do this, and you can get from this a first model discrimination, so regarding models that could do this. And then you can also go further and say, okay, in specific models, we have direct connections to certain high-PT searches, to lepton decays, to lepton flavor violation, to electric dipole moments, and so on, and analyze which specific models might actually still survive all the existing constraints. And this is not easy, but there are still some models that survive all constraints. And finally, you can also analyze the flavor structure. So instead of B2C, you can consider, for example, B2U, or instead of a tau in a final state, you can consider light leptons in a final state. And this is also what I will talk about in the following. So I mentioned form factors a couple of times. So they are the fundamental object, basically, that we need to predict semileptonic decays. And they parameterize, basically, the fundamental mismatch that we have between theory, where we formulate everything in terms of partons, so especially quarks, versus experiment where we measure only hadrons, right? So we have confinement in the standard model. Well, not only in the standard model, we have confinement for all we have seen so far. So what we have is basically matrix elements like this, where we have hadronic states in the initial and final state, and then we have a quark current, and somehow we need to parameterize this object. And what I write here on the right is just the most general matrix element parameterization that you can write, given the symmetries that we have. And the symmetries are the Lorentz symmetry and the parity and time reversal symmetry of QCD. And when you do this, you find, in this case, for this matrix element, two objects, this F plus and F minus. And these are now functions that depend on Q squared, which is the invariant mass of the lepton pair in the process. But they are real functions and they are scalar. So you have two functions as the most general parametrization of this very complicated object. And how do we obtain these functions? We can either try to obtain them from theory, for example, on the lattice or from Latcon sum rules. And here, basically, the question is how precisely can we do this? And simulations with heavy quarks in the initial and final states have only become available over the recent years. And for B2D star, for example, we are still waiting for the first official results that do not just consider one very specific point of Q squared. On the other hand, you can try to determine them experimentally, for example, in semileptonic transitions. Here, the problem is that you cannot get a normalization because you only have always the product of the CKM factor that you also want to determine and the form factor. And you can have suppressed form factors that are not visible in the experimental data. And of course, you need to make an assumption, for example, that you're in the standard model to do that. And then you have a problem when you want to parametrize new physics. So these are the two approaches that we have, basically. And regarding these functions, the main issue is the Q squared dependence that we have. So the range of Q squared can be large. For example, in B2D, we have something like 12 GeV squared spanned by Q squared, depending on the on the configuration of the leptons and the D meson in the final state. And calculations typically give you only 1 point or a few points in Q squared for the form factor. So it's crucial to know the functional dependence of Q squared on Q squared. But this is really where the discussions start, and different theorists have different preferences, and therefore it's very important to give as much information as possible independent of this choice. Especially when you do an experiment, it's very important to not commit to one specific set of form factors for everything, because as soon as somebody wants to improve the form factor description, for example, you will not be able to use your data anymore if you only publish results that are specific to one of these parametrizations. In the following, I will discuss two different parametrizations. One is the so-called BGL parametrization, and the other I call heavy quark expansion parametrization. And both of them use as a conformal transformation to formulate the Q squared dependence as dependence on a parameter Z that is given by this expression. And the important point is that the modulus of Z is typically much smaller than 1 in the physical region of the semileptonic process. For example, in B2D, it's smaller than 6%. So this is, in principle, a good expansion parameter. And in the BGL transformation parametrization, after Boyd, Grinstein, and Lebed, the approach is that we parametrize the form factors in a very general way. So we only consider the analytical structure that we can infer basically from the spectrum of the transition we are considering. And then we make all the poles and cuts in this analytical structure explicit. Yeah, so basically everything that can, so essentially we remove all infinities, yeah, naively speaking. And once we have done this, the rest we can just Taylor expand in this Z parameter. Yeah, and this you see here. Yeah, so here the sum is just a Taylor expansion, and everything in front of it might have still poles and so on, but they are made explicit. So this part, starts with a constant, basically. Yeah, so there is no 1 over z in this expansion. And then importantly, you can apply very generic QCD properties like unitarity and crossing symmetry to write the dispersion relation for this process. And dispersion relation basically relates a Platonic expression with a hadronic one. And the Platonic expression is calculable perturbatively. And once you've done this, the fantastic thing really is that you do not only have a Taylor expansion here in Z, where I said Z is something like at most 6%, but you get an upper limit on the coefficient. So the modulus of this coefficient cannot be larger than 1. And this means that after writing 2 or 3 terms in this expansion, you know that the next term will be very, very small. And you can actually calculate the uncertainty you introduce by truncating your series. And this is a fantastic feature of this approach. You can apply this, for example, to do a standard model analysis to extract VCB from B to D star decays. And we did this a couple of years ago. And we analyzed the available Bell data sets with BGL form factors. And we find that these data sets are compatible. You have to be careful with systematic uncertainties. And we expand all our form factors up to z squared, which is not necessary in the sense that otherwise we couldn't fit the data, but it's necessary to take into account the higher order uncertainties introduced by these terms. And we find actually a 50% increased uncertainty compared to the original experimental analysis in a similar framework. And then we can determine VCB from this. And you see, this is something like 2.5% uncertainty here on VCB, which is not too bad. And we can use this to predict this RD star ratio in B2C tau nu transitions. And this plot here is essentially the update of the x-axis of the plot of the VCB puzzle that I've shown you before. And you see here the inclusive determination, here the one from this work from Bell 2018, here 2017, and here the combination. And you see that all these extractions, so there is some tension between this one here and this one here. But if you take this data point and this one, and then this as a third one, which is the average of these two, the tension is just something like 1.5 sigma. So the VCB puzzle is significantly reduced by being able to reanalyze the experimental data in this BGL framework, which has become only possible because Bell published their data in a form factor independent way, starting from 2017. The other parameterization, the heavy quark expansion parameterization, is not quite so general. But here we use additional information from the fact that the B and the beauty and the charm quarks are very heavy. And in the limit where they are infinitely heavy, we can actually parameterize all B2D and B2D star form factors. So this is order 20 by just one function. And this is amazing, but of course, this is not a realistic limit. So we need to systematically expand in 1 over m. And this is possible. And we can do that and still have a more constrained system of parameters, basically. So the overall number of parameters is lower than when we would parameterize every form factor in the BGL framework. So you have still some relations between form factors. And this is actually necessary for new physics analysis because we do not have enough sufficient information to determine all the form factors yet from the lattice, for instance. The so-called CLN parametrization after Caprini, Lelouch, and Neubert uses this framework up to 1/m and includes IFRS corrections and some approximate constraints from unitarity. This more recent approach from Bernlochner et al. Uses the same approach, but they updated everything and use a consistent treatment of correlations, which is important here. But the problem with both these approaches is that they clearly contradict lattice QCD. And this is true for B2D and for B2D star. And this is dealt with by varying parameters that are actually calculable in their approach when you expand only up to 1/m. But the problem is, if you do that, you leave the grounds of a systematic expansion in 1/m. So the related uncertainty remain basically lambda over 2mc squared, which is something like 5%, which is insufficient for precision analysis. And it turns out, however, that you can include systematically also the 1/mc squared corrections because the structure has been calculated a long time ago. And we have nowadays enough theory information to constrain this sufficiently to get a good handle on the form factors. And this has been done in 2 of our papers over the last 2 years, basically, or 2.5. So what we do is okay, let me just mention before again. So in the standard model, you can just do the BGL fit to data. You need the form factor normalization, and then you can extract VCB. So this is all fine, and we did this as I've shown you. But if you want to allow for new physics, this can affect the Q-squared dependence of your form factors and also introduce additional form factors. So you cannot generally disentangle basically this new physics from the form factor shapes. So you cannot use the experimental information to determine the form factor shapes anymore. So you need really the form factor shapes from theory. And this is what we're doing here. So we use all available theory inputs. So we use lattice QCD, we use the unitarity bounds I mentioned already. We use Lightcon sum rules, which is a point of concern for some people because this is related at least to sizable systematic uncertainties. But overall, we find a very consistent heavy quark expansion at 1/mc squared and a much improved transcription to what we found previously. And also in this case, we can extract RD star, and this is a purely theory. So this is really determined from theory here without experimental input and is compatible with the other value I've shown you before. And this is an example for one of the form factors. And in orange, you see a band that I call 3 to 1. While in blue, we have the same fit to the same data, but in 2, 1, 0. And these numbers indicate the order of Z to which we go at each order in 1/m. So this is 0th order up to Z squared or Z cubed, and so on. And here you have a lattice data point, and the others are Lightcon sum rule results. And this works very well. And to check the robustness of our predictions, what you see here is theory predictions. So this is not a fit. So the blue boxes and the yellow boxes here are theory predictions, and these are overlaid with the Bell data. Yeah, so not a fit, really our predictions versus the observed data without doing anything. And you see that this works perfectly. And you see also that here the uncertainties are actually much larger on the experimental side. So this does not really improve our form factors if we include this data set, while here it's comparable. And this is the Q-squared dependence, basically. So this is the differential rate. Importantly, we extract also a compatible value for VCB from between different approaches we use for the form factor parametrization. And on this slide, I show you to really emphasize the importance of including the uncertainties related to higher orders in your form factors. So what I show you here are ratios of form factor parameters. So these are BGL coefficient. These A's and B's and C's are BGL coefficients. And this expansion I've shown you before. But ratios of these are shown here, right? A1 over A0 and A2 over A0, etc. And the yellow bands or areas are what you get when you just use experiment plus unitarity. So no theory input, no lattice calculation, no light consum rules, nothing. And you see that the uncertainty here, especially for this form factor, which is the vector form factor, is much larger than from the theory predictions. While here again, they become compatible or comparable. So you learn something also from including experimental data in the standard model. And then in red, you have the heavy quark expansion theory fit in this 2-1-0 approach. Yeah, so with lower orders in Z. And you see how massively you underestimate your uncertainties when you only use the lowest order you need to fit all the data. So you need to include somehow the uncertainties from higher orders. This is really essential here. Then let me talk, because this is really a hot topic at the moment, and several lattice groups are working on the first analysis of B2D star form factors that does not just simulate data at maximum Q-squared for one form factor. This is what we had so far, but for several form factors at several points in Q-squared. And I show you here two preliminary results. So here, this is from the JLQCD collaboration, but the scale is so high, the scale is here such that you cannot really see the slope of these points and so on. And this is really preliminary data that, so there's no continuum limit yet and so on. So I focus on the two plots on the right. And this is from the Fermilab Milk collaboration, this plot. This R1 is a ratio of two form factors that they predict on the lattice in red here. So they have these 3 points, and then they use the BGA parametrization to extrapolate this to higher orders in W, which is another way of writing a Q-squared dependence, but higher values correspond to lower Q-squared values. On the right, you see our theory prediction here in red. And in yellow and orange, you see our BGL fits that are basically determined only by experimental information. And you see that these two fit perfectly on top of each other. And you see that comparing the left and the right plot here, they have the same scale. That you see here the slope that is a bit surprising. But overall, the compatibility is not too bad of these points with this here. So they are a bit high here, maybe compared to our previous extraction, but this is something like 1 to 2 sigma. So there's not a big issue here, but an issue you have here. So this is another ratio of two form factors. And here, the scale is actually not the same, because the plot on the left ends at this dashed line where you actually cut away part of our theory prediction. So the comparison of this red band and our theory prediction in sort of dark blue grayish, and the experimental information basically extracted from here in blue, this shows really a significant tension. So there are 3 sigma or even more between the two. So I've waited, or many people waited for this lattice simulation for a long time. But at the moment, it seems really this has still some issues, let's say. And it's not just a discrepancy between our previous theory extraction and the lattice values, but especially also between the experimental extraction of these ratios, or of this ratio, this R2 ratio, and the lattice values. Yeah, so there really seems to be an issue. In the remaining, let's say, 10 minutes, I want to talk about 2 projects, 2 more recent projects that we have done. And the first is an analysis of flavor universality in B2D star, E nu, and mu nu decays. So far, the results of this B2D star decays were always flavor averaged between electrons and muons. But the Bell collaboration actually presented separate 40 by 40 covariance matrices for electrons and muons. And they presented the result for this R ratio, RD star, but between electrons and muons and not between taus and light leptons. And they find this very well compatible with 1, which would be the standard model prediction essentially. So the question we asked was, can we learn more about flavor non-universality from these data? And we encountered 2 issues here. The first is that the correlations between the electron and the muon data are not given explicitly. They sort of exist because they also have been used to determine this uncertainty here of this ratio by the collaboration themselves. And it turns out actually that you can also construct them from the data given in the paper. But this is a non-trivial thing to do. So what you end up with is basically an 80 by 80 covariance matrix between the electron and muon data in B2D star. But these covariance matrices have another issue, and this is actually a physics issue, and that is that they should be singular. And that is because the way that the data are presented is such that they bin the same data in 3 or 4 different ways, actually in 4 different ways, always in 10 bins, but it's the same data. And that means that the sum over all, let's say, rows of data must give the same number of events. And they do, but that means that you can basically calculate 1 bin in each row from the sum of all bins in another row and the 9 first bins. And that means that your covariance matrix should be singular, but it is not. And it's also not close to being singular. And this is really a problem because the correlations in these processes really determine in the end the precision you can get. And so they are very important for this kind of analysis. And what we did anyway to analyze this data was to extract first angular observables for the angular bins, or from the angular bins, because it turns out you can actually parametrize in full generality, including new physics, these 30 angular bins that the collaboration presents in terms of 4 angular observables. And we did this both for electrons and for muons, so it's 2 times 4 instead of 2 times 30 bins. Yeah, so we have, in the end, 8 observables instead of 60. And this you can do completely model independently, and this works fine. And then we compare with the standard model predictions based on our form factors at 1 over mc squared that I just presented to you. And what we find is a 4 sigma discrepancy in the so-called forward-backward asymmetry. And this you see here. This is the experimental data, and this is our standard model prediction. And not only you see that this is significantly away from 0, but you see also that the standard model prediction is actually significantly away from 0. And that means that in this observable already now, the muon mass becomes relevant. Yeah, so naively, you would say that the difference between these two should be 0 if you, in the standard model, if you ignore the lepton masses, which are very light. But it turns out that the muon mass is actually already has to be taken into account because we achieved such an impressive experimental precision that the difference here is comparable to the error to the uncertainty of the experimental analysis. And the same is true for this FL tilde observable that I haven't introduced here. While all the other observables you see are actually very well compatible with their standard model predictions. And the problem is now that we do not really know whether this is now because the covariance matrix is not correct, or whether this is because there's really new physics. So this is a problem that we asked collaboration to address, but the authors of the study don't really want to. And but in principle, this is of the same order like the B2C tau nu anomaly, right? So this could be potentially extremely interesting. And finally, I want to say a few words about non-leptonic transitions. So here you require the same form factors, but non-leptonic transitions are actually much more complicated because you have 2 hadrons in a final state and there can be extremely complicated dynamics. What we did was to consider from a theoretical point of view the simplest case that you have. And that is, and these are these 2 transitions, so BD, meaning a neutral B meson going to a charge D and a K, and the BS going to a D sub S and a pion. And these are theoretically the cleanest, let's say, because there are 5 different quarks involved. So all quarks in this game are different, and this excludes a lot of topologies that make your life extremely complicated in these in this type of decays. So for those who know what it is, for example, you do not have penguin topologies. You do not have annihilation topologies. You do not have divergent hard scattering contributions and so on. So this is why we looked at these modes here. And they are used phenomenologically actually to extract the production fractions between B sub S mesons and B sub D mesons at hadron colliders. And this was the reason why we looked into, also a reason why we looked into them. And because they are so relatively simple, their amplitudes are completely dominated by these form factors that we extracted before. And actually, so usually you encounter, when you try to calculate these processes, you can encounter infinities at a 1 over m level. And this is not the case here. So all this together makes for a rather let's say, reliable theory prediction. But it turns out that we can very nicely predict ratios of two of these decays. You see, this is the lower part here, and you see that the experimental, this is always the ratio between the experiment and the theory prediction. And you see that for these ratios, this works actually very well. But if you look at the normalization, you have systematically too large experimental branching ratios compared to the theory prediction. And this is a large effect. This is something like 30%. And these are really leading decays. Yeah, so this is a significant fraction of the B lifetime, for example. And it's really a big question why that is. In principle, also in this case, it might be new physics. You have a lot of constraints, and especially from collider constraints, you can almost exclude all scenarios that people have thought of so far. But even if it's not new physics, this is a much larger effect than we would have expected for our theory prediction. So we will learn something important, whatever the resolution of this puzzle is. So this brings me to my conclusions. So B2C transitions are an important playground for indirect searches for new physics and are important for determining standard model parameters. And in this game, form factors are really the essential ingredients to be able to do precision physics. And for these form factors, I told you that the Q-squared dependence is critical. So we need form factor independent data. And how crucial it is to include the higher order theory uncertainties to get reliable results. I've shown you this BGL form factors that are model independent and where you can really calculate the truncation uncertainty that you introduce. And we used these form factors to analyze B2D star and found a reduced VCB puzzle and a somewhat lower RD star prediction than a previous analysis found. But for new physics analysis, you really need form factors determined from theory inputs. And 1/MC is really not good enough for precision analysis. So I've shown you the first analysis that is systematic at 1/MC squared and provides all the relevant form factors in B2D and B2D star. And we found a VCB value consistent with BGL. But we also found lepton flavor universality violation in these B2C L nu decays at something like 4 sigma. And as I told you, we cannot be sure that it's new physics because we have these experimental issues that need resolving. And finally, I talked a little bit about non-leptonic decays, and also here we have a large tension. And one thing that is important here to clarify this is really to perform somewhat profane branching ratio measurements. So these are sometimes considered a bit trivial, but also here it's really important to do them and to do them with better precision than what we had so far. And for that, really, I would conclude basically with a central lesson that given the precision we're trying to achieve at modern colliders and in theory at the moment, it's really essential that experimentalists and theorists meet very closely together. Thank you very much.
Thank you, Martin, for this fantastic talk. It's been very stimulating, really stimulating. So now we are open for questions, and I have a couple, but I'll first allow the other organizers. We'll give them the chance to ask one, if this so desire. Apparently, they will let me ask the question first.
I have a small question.
Okay, Robert, I was waiting for you.
More. Very nice the talk, Martin, by the way.
Okay.
So I was wondering, is any, because you talk about the lepton universality, that is a possible way to explore, but is it a way also to detect, for instance, more than, I mean, going more in the side of the model building point of view to see effects related, for instance, with leptoquarks or other type of particles that mix lepton and hadron sectors?
Yeah, so the problem is because of these experimental issues. So the idea of this analysis was really a new physics analysis, and to go exactly into a little bit, at least, also into model building, etc. But because we are not sure that we can trust the data, and for sure something will change, if in case they will update these correlation matrices and so on, we did not do a detailed analysis. What we did was to see which type of new physics can contribute to which observable. And we found that it is possible to have an effect in this delta AFB observable without seeing large effects everywhere else, which is not trivial. Yeah, so this is possible. And the thing that would work best, but we did not discuss specific models, but we only discussed operator scenarios, right? So sort of still model independently what type of structures we would need to have such contributions. And what would work best basically would be a right-handed vector currents. And the other possibility would be to have tensor currents and pseudo-scalar currents, which are anyway typically created together in specific new physics models. In that case, if you only put these two couplings, you cannot get the central value of what we see, but you reduce the tension here from 4 point something sigma to something like 2 or so. But this is as far as we went, because we said, okay, first we really need to see what the situation will be after the experimental information has been updated.
Okay, so sorry, yeah, there was I got distracted on the last part when you were mentioning the operators. There was a small earthquake, small tremor, but I got slightly distracted. So what were the operate? No, nothing serious, I hope. So what were the operators that would fix AFB?
Yeah, so in terms of minimal couplings, right? I mean, you can always put several. So in terms of minimal couplings, what would work best are right-handed currents, right-handed vector currents.
Okay. So not related to
a right-handed vector current on the quark side with a left-handed vector current on the lepton side. Yeah. And the other would be a combination of pseudoscalar and tensor couplings.
Right. So nothing comparable to the operators that, in principle, are favored by the B meson anomaly. Right?
Well, exactly. So if you look into like the everybody's favorite scenario where you just put a left-handed vector current and rescale everything, right? This is like the sort of simplest thing you can do, but this AFB is actually a ratio. So any modification just by a factor of the standard model contribution would cancel an AFB. So this cannot be the only coupling you have. You can improve, let's say, your scenario, for example, if you have a right-handed vector current and then you add in addition a left-handed vector current or so. But it cannot be the only new thing you have, a left-handed vector current, because this would not contribute at all to AFB.
Mm-hmm.
Yeah.
And what is delta X that I see there that isn't very nice either?
Oh,
It's
delta
delta
X.
X8.
No,
It's
but
delta
this
X8.
is perfectly within statistical expectations, right? So you have here, so delta X is are the partial branching fractions normalized to the total branching fraction. And so here, this is something, I mean, this is not even 2 sigma, but it's like the only one that is so far, right? While everything is compatible and 1 in 10 is fine, right? So
yeah,
I think this is not so much of an issue. So this is the
yeah,
only one that has really a high significance. Oh, and I want to say, so in principle, if you say, okay, you only look at delta FB, you could have something like a look elsewhere effect, right? So we are cherry picking just the one observable that is anomalous while everything else agrees. But also if we like fit all observables that we have, we find something like for sigma tension with a standard model. So also in the global fit, this is not just the one observable.
Right.
But this is the only one that really gives this large effect. Yeah, but it's not that the global fit is good and then you have just one observable that is bad, but the global fit is also bad.
I see.
And because there was this issue that the correlations between electrons and muons were not given, we tried to check whether we could resolve this issue by modifying the correlations between the muons and electrons. And we allowed for the basically most conservative scenario that we could imagine. And this is not possible to remove this issue by that. So this is not, so this first point here is not the reason for this tension. You can a little bit decrease the tension maybe, but even for a rather crazy scenario, you would still get over 3 sigma tension. Yes, and this was really the most extreme we could think of. So allowing for like minus 100% correlation between the systematic uncertainty between electrons and muons, which everybody assures is not realistic. So the correlation should be really small, but it should be like a couple of percent maybe. Anyway, yeah.
Interesting. I don't know if there's any other question from the other people attending. We don't have any question on the YouTube channel. But let me go for my first question, which was related to slide 12. Which is a BGL, this initial determination that you do of VCB. So there you are doing a fit of many parameters, right? And one of them is VCB. So what else is involved here?
So basically, what you need to describe B2D star L nu data in the standard model are 3 form factors. And all of these have 3 parameters. So we go to z squared, so 6% squared, so already rather small, right? So in this, in this expansion, 3 parameters, we have n equals to 0, n equals to 1 and to 2. So we have 3 coefficients.
Right.
But then there is one like one parametric identity that relates 2 of these form factors at one value of q squared, and that removes another parameter. That means we need 8 parameters to, in full generality, describe these 3 form factors, and then we have VCB. So we have 9 parameters here.
Okay.
And we have 40 data points from the 2018 analysis, and we have, I think, also 40 from the 2017. So it's like 80 data points and 9 parameters.
Right. So then you mentioned something about this this tension between the inclusive and exclusive determination being reduced. But then what I didn't understand was how you did it, right? Because I said, okay, we average this one and we average this other one, and then we combine that, and then it doesn't look so bad, right? So that's what I didn't understand very well.
Okay, so for B2D, which I haven't shown this analysis, but we did also B2D, and Gambino et al. Did this previously. This value is quite a bit higher than it used to be. And you see here, these two are not really in contradiction, the inclusive and the exclusive value, right? And then for B2D star, there are 2 data sets. And the red one is when you analyze them together, and these 2 are the individual results. You see one of these 2 is also not in tension. Only this one is in tension, right?
Yes.
And what I did was to average this one from B2D star. So the 3 modes, basically, B2D star, B2D, and B2XC, so the inclusive mode. And then the tension is something like 1.5 sigma with our uncertainties. But I told you, like, okay, so for B2D star especially, so what was done experimentally, they said, okay, we just take the form factors and we add parameters until we get a good fit, which is fine, right? But of course, the parameters that you don't need necessarily to fit the data can still give you uncertainty. So just because you can fit the data doesn't mean that this is that the form of the form factor is general enough to accommodate all fluctuations, right? And if you instead express all form factors and you go up to z squared, because you say z cubed is so small that this cannot possibly, and we actually check this explicitly, and it cannot possibly affect our analysis significantly, then the uncertainty of VCB becomes 50% larger. So this is, yeah, so, and thereby the tension becomes smaller, of course, if your uncertainty is larger, right? Another aspect was actually that our central value is also higher than what the experimental analysis gives. And the reason is that the central value that the experiment gives is determined by just fitting the experimental data with statistical uncertainties, not the systematic ones. But the systematic ones are very Q-squared dependent, and there is especially one area in Q-squared that is extremely important to determine VCB. And therefore, if you do this differently, you get basically a 1 sigma shift in the central value of VCB if you do the baseline fit differently and you include the systematic uncertainties from the start. And this was the other aspect. So we have a larger uncertainty and our central value is 1 sigma higher. And therefore, the tension is significantly reduced.
Right. Right. Okay. And then what is the impact that this new value of VCB, what is the impact on the B meson anomalies? Right?
On the B meson anomalies, there's very little impact in a sense. Well, okay, so I think we extracted now RD star more reliably. And all analysis that includes these more recent data so these were the analyses that entered the like theory average that href did, that you still find on the href page. And now you see, when you include the 2018 data that was not available back then, the values go down. Yeah. So all these values are much smaller, or not much smaller, but quite a bit smaller. Yeah. So if you would do a new href average in the same way they did it before, it would go down like 1 sigma or so. So in that sense, it affects the anomaly because it becomes more significant, because the difference or the experiment is at high values for RD star, right? So the significance becomes a bit larger, but this is not a lot. If you have half a sigma more or less, I don't care. Before, if you have 3.5 or 4, will not convince you that this is new physics if you don't believe it, and it will not convince you otherwise if you do believe in new physics. Yeah, so I don't think it really affects this a lot. And the VCB value, of course, does not enter here, right? Because it's a ratio of 2 branching fractions. So VCB cancels in this. So it only depends on the shape of the form factors, this prediction, not on the normalization.
Right, yeah.
Or not on the normalization of all of them. Well, there are ratios of form factors that appear only. And the other thing, in another sense, it does not affect the anomaly, in the sense that this effect that we see here is, first of all, not affecting the branching ratio. Yeah, so this is still rather compatible with our prediction. Second of all, it would be too small to account for the RD star anomaly. Yeah, so you cannot explain the anomaly by reducing the branching fraction of the light leptons, basically. Yeah, in principle, you could think maybe it's not the numerator, it's the denominator, right? But we have not found any indication of that. So this is not a way to explain the RD star results. So this is something in addition, let's say. Yeah, so it might be still something that also enters in B2C tau nu, but because the effects are smaller, you will not so easily see it there, right? Because there you have much larger uncertainties than in B2C L nu with light leptons, and you don't have such detailed differential analysis or so, right? So the database is much weaker for B2C tau nu.
Okay, super. Okay, I don't know if there's any other question from the other hosts. Apparently not. Apparently everybody's very happy.
I have one very short. No, because in you I mean, for the future, which other experiments are planned to help in the determination of the parameter? Because now you present Bell, that is the one with the largest, but are there other experiments planned, like to in the way that?
Right. So this is a bit of well, okay. So first of all, of course, Bell 2 is running, and they should be able to do a much better job here. Also, LHCb actually started measuring semileptonic decays, which is impressive because this was not foreseen when LHCb was proposed. They thought they couldn't do it, but they can. But there you have the problem of finding that you do not have absolute branching fractions, but they can measure the shapes very precisely. And there they started doing this. They measured, for example, B sub S to ds and ds star L nu, or mu nu, in fact. So LHCb and Bell 2 are sort of the key players here for these modes. In principle, Right. So we would like to see, well, not refined, but well, actually, we will see a refined analysis of B2D star L nu by Bell with a certain tech method. So this is work in progress, and I hope, and they probably will publish this year still. Because they, while building Bell 2, basically they improved their tech methods and so on. So they have now a sort of a better way to analyze the old data. And so we can expect something also in the short term. But Bell 2 actually already released first results, but they are not yet at this level of precision. One thing is that in principle, of course, you could do this also with Barbar data, right? Because Barbar and Dell were famously competitors and so on. The problem is that even in their latest analysis that is appeared, I think, 2 years ago, they did not publish form factor independent data. So we cannot analyze it the same way we analyze the Bell data. So in that sense, Bell was really exemplary. Yeah? So I almost only mentioned the problems, but like these data are very close to exactly what we want. Yeah, all the correlations, no reliance on form factors and so on. So this is very nice. These data sets are really nice to have, and we can learn a lot from them. And of course, if they would really provide an updated correlation matrix that shows the properties that it should have, this analysis would be much more exciting. So this was actually quite frustrating to work on this, because we were always like, this is, in principle, would be so cool, right, to see this, but we always have to say in the same sentence, yeah, but we're not sure, you know, we don't know. Yeah, that's what it is.
Okay, thanks.
Sure.
Super. So I guess there are no more questions. So I'd like to thank Martin once again for this fantastic webinar. And before we leave, I'd like to remind all the viewers that we have our next webinar will be on the 26th of May, and we're having Michele Dodo. So please don't miss it. All right. So we'll see you at that time. Thanks, Martin, once again.
Sure. Thank you for inviting me.
Okay. So